Test. Okay. Feel free to correct me. Thanks. Is Steven coming? I have to give him the copy card. Because I stole it from him. Test. Yes. We still have like 250 on it, so we're nowhere close to running out. Yeah. Yeah, I'm not surprised. All right. Is this working, or do I need to? If I move the mic here, could everybody hear, or no? Should I move it closer? Okay, I'll just hold the mic. Hello. All right. Hi, everyone. Welcome to today's lecture. As you can see, I'm not Dan, nor am I Mickey. So they will not be giving either of these lectures. Dan is traveling. Mickey is, I think, doing some work. So today I will be the lectures. My name is Sean. I'm a TA for this class. I've TA'd this class for a couple of years now, and I don't know. I just kind of like the information, and I appreciate you all coming to lecture today. I understand you all have a midterm tonight at 7 p.m. I hope you all are ready for that. I think you guys are all in good shape. Just breathe, relax, attack with all the problems. You're all ready. All right, you're all ready. But today we're just going to move on forward with more material. So just a quick thing about the news. I don't know if any of you saw, but this past week, Jack Dorsey from Twitter said that Twitter's going to ban all political ads on its platform. Yeah, that's actually really interesting when you think about the ethics of big companies and what they're doing, because Facebook has taken a staunch opposite stance of saying we're just going to allow anybody to post anything with no fact checking whatsoever. So very interesting to see how that kind of dynamic is going to play out in the future. So yeah, keep that in mind. Just go to Facebook. Why did I put that? Why do I trust what? Well, I mean, he said he was, right? So we'll see if he does. So, yeah. His word is always... They said they're going to use artificial intelligence methods, so you should know, as a CS major, how robust that actually sounds. So we'll see what that actually amounts to. Yeah. I don't believe it either. Anyway, okay, so let's review where we were last week. So last week, or I guess in Wednesday's lecture, we ended with caches. Okay, so caches was our way of kind of expanding our way out. We understand how the entire data path works already. We understand from the very beginning. We have code, it gets down to RISC-V, that goes down to bits, we have the CPU. We understand the whole thing by now. right? But the whole reason why we introduced caching was because we wanted to make things faster. Okay, the dynamic between going from memory all the way to your CPU is really, really slow, so instead we need to put something in between, and it kind of builds up our model. One thing that I want everybody to remember as we're moving forward in the class is that we're going to introduce more things to show how we make things faster. That's kind of the theme of the third portion of the class. How do we make things faster and faster? But the idea is nothing is fundamentally changing. Okay, before you even knew about caches, we told you, okay, there's a load word instruction, it uses some kind of address, et cetera, et cetera. Okay, but we never told you that in the middle there was this whole middle process. Okay, and then when we learned about caches, nothing changed. Okay, it doesn't change the way that you're feeding an address into memory, for example. There's just extra steps. The same thing is going to happen today. We're going to pull down another curtain in the memory model process of how things are actually working, but I want you to remember that nothing is fundamentally changing. All right, you still provide the same addresses, you still do the same thing. Nothing is changing. I want you to keep that in mind because things get a little bit hairy today. Okay, so in this class, we don't talk about okay ideas. We don't talk about good ideas. We talk about great ideas of computer architecture. And one of the greatest ideas of computer architecture is the memory hierarchy, right? So recently we've been focusing on like the top levels, right? We have our CPU with the register, and then last week we learned about these levels of caches that make things faster, right? And the point is, as you get further and further away, it's like less expensive, right? The closer we are, the more expensive we have to do here. And the farther we go, the slower it is, but we have access to more memory. So from now on, for the next 3 lectures, we're actually going to be looking at these 3 levels right here. Now we're at RAM, but like, what about RAM? Like, how does it actually work? I remember when I took this class, I always asked, like, whenever we write diagrams on boards or whatnot, we always say DRAM. DRAM is memory, et cetera, et cetera, et cetera. But, my computer has way more than 16 gigs of, memory on it, right? You're buying your 1 terabyte hard drive, your 500 gigabyte hard drive. Where the hell is, like, all that memory? Where is that even being used? So we're going to talk about that in the next couple of lectures. What does that even have to do with anything? Okay, so, yeah. It's the same thing, right? This is our memory model. We're going to bring it out, and eventually we're just going to expand further into this. Okay. Yeah. So let's talk about context for why we want to do this. Okay. Everything so far in this class, we've been making one fundamental assumption, and that is that there's only one thing happening at a time, right? There's one piece of RISC-V code. There's one program you want to run. You compile it, you link it, you load it, et cetera, et cetera, et cetera, but you're only running one thing. But is that reality? No. On my computer at any one time, I'm running Spotify and Finder and my terminal and Sublime and, my email. There's so many different programs running at the same exact time. Right? So it doesn't make sense for us to view a computer as only one program getting executed. So we need to think about how do we actually execute multiple things at the same time. So in the lingo of computer systems, we can generally call these things processes. Okay, so if any of you on a Mac, you can go into your terminal and write PS, and it would list out all the processes that are currently happening on your machine. And these are all things that your operating system, which is a piece of software in your machine, is deciding, like, how do we actually schedule these things to work? How do I get everything to execute? Okay, so there's one big problem with this. If you think about it, what was our memory model before? When I have a process, I have my 4 areas of memory, right? Code, static, heap, and stack. Okay, so I have one process that deals with that. And, if you think about it, code starts at the very bottom, right? And then it ends at, like, in this case, address 4, right? Then we kind of move on up and up and up. But let's say I have 2 processes. Okay, let's say I have Spotify running and I have, my email running. Okay, they both assume that their code starts and occupies the same portion of memory. Well, how do we mediate between those two things? Can they both actually share the same exact portion of memory? And how does this scale to hundreds of processes? If I have way more processes, are they all actually occupying the same exact portion of memory? Are they all using the same stack? Are they all using the same heap? It's kind of weird questions to think about, right? And if you think about it, with your 4 gigabytes of RAM or your 8 gigabytes of RAM, does that even make sense to scale? If one program needs to use a ton of RAM, cough, cough, Chrome, right, is using like 8 gigs of RAM, for example, your machine might not support 8 gigs of RAM. So how does it actually utilize more space than it thinks it has? So that's where the idea of something called virtual memory comes in. So we have all these hundreds of processes, and each one needs to behave as if it's kind of its own thing. Right? This is our model of how everything was working. You have your own thing, you have your own memory to work with, blah, 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 blah. So how do we mediate between all these factors? Okay, so I don't know if any of you have ever seen the show Arrested Development, but in that show, there's this character named Job, and he's a magician, and he always says, it's just an illusion. Okay, and I want to remind you that when we study virtual memory, the key word in virtual memory is it's just an illusion. Okay, the idea is when we are dealing with any processes, we give each program, we give each process its own illusion of memory to work with. Each process assumes that it has all of memory to itself. But in reality, it does not have all of memory to itself. And we have this whole module that ensures that everybody could assume that it works that way. Okay? So it's just an illusion, but it doesn't affect anything. We have to make no changes on the program's level to affect like what's actually happening here under the hood. Let's see, where's the pages? We're going to talk more about this later. One thing that's actually cool is that this idea actually predated caches, and it actually inspired the idea for caches later on, which is like, I don't know, it's kind of a cool timing thing. Yeah. Bring it closer to my mouse. Okay. Okay, so let's talk about this. Okay, this is our current model. Right, we have our registers, we have our kind of view of memory, right? They should look familiar to you, code, static, heap, stack, and then we give it an address, and that should go into actual memory, right? But the truth is, this is not what's actually happening. Okay, instead, each process, it's getting its own virtual address. So every address that you've ever considered up until today, we're going to call those virtual addresses. They're no longer actual addresses, okay? What happens is, they get converted to things called physical addresses. So Spotify is running on its own piece of memory. It's using its own virtual addresses. Oh, load word at address ABCDEFGH, right? But the truth is, it might not actually be able to go into ABCDEFGH. So instead, there's some guy here whose sole job is to say, oh, okay, you want to be working there? That's fine. You know, I'm actually going to have you work here instead. So it's a mapping between where the program thinks it's working between and where it's actually working in memory, okay? But the program does not need to know about this, okay? It assumes that everything works. Yeah. We'll get to where the cache fits in later. Yeah, we're going to build it up as to not like overwhelm with too many moving parts at the same time. One-way memory, blah, 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 blah. Okay, just another description of this, I guess. It's the same thing. Okay, so let's talk about address spaces. Okay, this goes into the same idea of the size of memory. If I have like a 32-bit machine, for example, you know you always hear it. I have a 32-bit machine, I have a 64-bit machine. Generally, you could assume that this is saying I have a 32-bit address space, which means what? Well, for byte adjustable memory, I can address 2 to the 32 bytes, which is about 4 gigabytes. 2 or 4 gigabytes. I forget the order of magnitude. Right. Okay. The truth is, your computer may or may not have 4 gigabytes. So therefore, there's a difference in the address space that each program sees and the address space that actually exists. The address space that the program sees is what we've been working with, 32-bit addresses. But the physical address space might be much, much larger. For example, my computer is a 64-bit machine. However, I have 16 gigs of RAM. Right, but 64 bits doesn't address, actually maybe it does address 16 gigs of RAM. All right, bad example. Let's assume it was a 32-bit machine. There you go. Then it doesn't match up nicely. Right, so the point is we have 2 different address spaces. Big picture here, there needs to be some kind of mapping between the virtual and the physical address spaces. So, here's an analogy that Mickey uses. Let's say, you know what, big fan of analogies in this class? Okay, let's say I want a book. All right, let's say Stephen is the librarian at the Library of Congress in this case. And I go up to Stephen one day and I say, hi, Stephen, I'd like to check out my favorite book, 50 Shades of Grey. And that's a joke, by the way. Not my favorite book. Okay, and I tell Stephen I would like that. That's the title. That's like the virtual address in this case. And Stephen is like, oh, okay, for sure. And I don't need to worry about what he does. But what he does is he looks inside the calling card and he figures out, oh, okay, well, 50 Shades of Grey actually corresponds to this call number. And he can go back into the little back, things at the library and extract for me what I need to get. Now, what if it isn't in the library? Then he needs to get it from, some external branch, like to bring it back into circulation. The appropriate analogy in here is that I'm a program, I would like some memory. I go to Stephen. Stephen says, don't worry about it. I'll take care of you. I'll give you the memory that you want in memory, right, in RAM. But if it's not there in RAM, Stephen will go to disk. Okay, so that's where your hard drive will come into play here. And we're going to build on this. All right, so what happens? All right, I have this stack, heap, static code, blah, blah, blah. So we're going to introduce a new terminology here. We're going to call it pages. Just like how for a cache, a block was just a unit of measurement for bytes, pages is just another unit of measurement. They tend to be much larger than blocks, though, anywhere from 4 kilobytes to 10, for example. Okay, they're much, much larger to work with. You should consider it like space of memory that you're allowed to be using. Okay, so this is what our program sees, right? Code, static, heap, stack. And by design, we'll say, okay, this computer will support 4 kilobyte pages, for example. Okay, so what we're going to do is we're going to divide up everything into these pages. We're straight up going to split up virtual memory into Where's one page of data? There's 2 pages, 3 pages, 4 pages, 5 pages, et cetera, et cetera. And then we're also going to divvy up physical memory into the same, kind of increments of pages. And therefore, what's going to happen? We're going to somehow map each portion of virtual memory to its corresponding area in here. Okay, so let's say hypothetically I have a program that's going to use some part of the stack. Okay, well, I can't give it all of the stack. And if you think about why, it should kind of make sense that maybe a program really needs a lot of information. Right, so the stack might grow over time. So what we're going to do is we're going to say, okay, great. If you work in this area of your virtual memory, that's actually going to correspond to a working area of memory right there in physical memory. It's just somewhere else. We don't really know where for now, but it's just somewhere else. Does that make sense? We're just telling it your working space is not actually where you think it is. It's getting mapped somewhere else instead. And this can get scrambled anywhere here. Okay, so we're just dividing up memory, and then we're mapping it somewhere else. Okay? Straightforward enough for now? Any questions? All right, cool. It's just high level for now. We're going to delve deep soon. So, this makes more sense in the context of 2 processes. So if I have 2 processes, I divvy up all their memory, and now I interleave. I don't want to really step all through all this, but yeah. So, this kind of brings the picture more together now, right? If I have 2 processes who each have their own illusion of how virtual memory is working, how does it actually work with regards to physical memory? How can they actually share the exact same address space? Right? If they both want to use the stack or if they both want to use the heap, they physically cannot map to the same address. It's impossible for both of them to share the same piece of physical memory. But they can share the same piece of virtual memory. Right? If process A uses this portion of the stack, okay, that just corresponds to some other area in here. Physical memory does not correspond to the same organization of code, static, heap, stack. Okay, it's just mapped somewhere else. So the point is, you want to work in the stack here? Okay, great. You can work here, and process B could also work at the stack here. But they'll just get mapped to different places to ensure that they will never collide with each other. And this brings in a very good point. This prevents processes from overriding each other's memory. It provides a sense of protection. If processes shared the same exact set of memory and there was no real mapping, the problem could be is that one process could start writing to memory and it starts overriding another process's memory. So by having this mapping of pages from virtual to physical addresses, we're ensuring that no 2 processes will ever touch each other's memory. Yeah.
I have 2 questions. So the first one is do each of these processes have their own unique tag?
We will get to that.
And also the second question, what if one process needs to modify some area of memory because it only knows virtual memory, right?
Mm-hmm.
It needs to modify memory that say another process has.
So processes are not allowed to touch each other's memory by definition.
Okay.
Yeah. So processes are completely independent things. They don't even know that each other exist. Okay. By the way, if you're more interested in how processes work and how your computer schedules a processes run, you should take 162. It delves very deep into the theory behind how these things kind of work. Okay, so our question now becomes one of, well, now that we understand kind of what we're going for, how the heck does this mapping procedure actually work? Okay, I have virtual memory, I have all these blocks that I'm divvying it up, and they're getting mapped in reality to somewhere else, but who is actually taking control and, who is keeping track of this? How am I even ensuring that these guys aren't mapping to the same block in physical memory? Who's taking care of this? So, we're going to walk through this. It's going to get a little technical, a little nitty-gritty here. It's very, very similar to how we break up the addresses in a cache, but it is so much simpler. Okay? It is definitely nowhere near as complex. Okay, why? So what we do is if we take the address itself, and we break it up into 2 fields. Does that sound familiar? Right? Yeah, we're breaking it up into 2 fields. But this time we only have 2 fields. Okay? We have the offset, which is straightly analogous to the offset in the caches, and then we just have the remainder of the bits, which we just call it the virtual page number itself. So, in a cache, the number of offset bits is determined by the size of the block, if you remember. Who can tell me, for virtual memory, how big do you think the number of offset bits will be here? The size of what? A page, right? Because I want to be able to index into each page, because that's how I'm divvying up my memory one at a time. Okay, so I will just take log base 2 of the size of my page, right? If you want more equations, if you're really all about that, right? And the rest of your number is just the virtual page number. We call it the VPN. This is not the same as the VPN that you do to access Facebook in China, for example. Okay, it's something different, right? So there is a mapping that we will use. We will feed the address into some unit. It will break it up into the offset and the virtual page number, and it will do some kind of mapping operation. Okay, what is that mapping operation? It is very simple. It is just a table indexed by the virtual page number. So therefore, if I have an address that ends up with page number 0, virtual page number 0, it will straight up look at the 0th element of this table. And that will give it the corresponding physical address. That's it. If this corresponds to physical page 10, it will look at the 10th entry. That's it. There's no sets. There's none of this business of ways and blah, 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 blah. Nothing. It's just a straight up index into the table itself. Okay? Now, what's important to realize is that the offset does not change. So the diagram on the next slide is actually much better in my opinion for this. Okay, so we break it up into the page number and the offset. And what it does... Okay. What it does is it will go inside, it will address using the virtual page number, and then from there it will extract a physical page number. Okay, so let's say hypothetically you're at some portion of the stack. Okay, and that corresponds, that'll give you an address that when you break it up, it corresponds to virtual page number, 15, for example. Okay, so therefore you will index into this table, look at entry 15, and in that table there will be a mapping. It will straight up tell you, oh, okay, you want virtual page number 15. That actually corresponds to page number something. Let's say hypothetically the OS tells us that it's page number 10. Okay, so therefore what I will do is I will just take out 10 and then recombine it with the same offset. The offset does not change between the physical and virtual page numbers. And that should kind of make sense. If, let's say, for example, this is my page, and I want to access halfway through the page, okay, that shouldn't mean that on my actual physical page that I'm working on, I'm all of a sudden living somewhere else. If I'm working at a byte that's halfway down my virtual page, I'm working at a byte that's halfway down the same physical page. It's just the placement of the page that differs. Does that make sense? So we just take the VPN, we index in, we get our PPN, and then we append that to our offset, and that gives us our new physical address. And now that I have my physical address, I can go to memory exactly how I did before. So you can just black box all of memory, caches, all L1, L2, all that crap. Point is, once I have the physical address, everything proceeds exactly as before. Exactly as before. There's just an extra step before any of that. We need to translate the address first. Cool. So there's a couple of extra bits here that we're worried about, right? So one of these things, we'll call it like a valid bit. So obviously, I don't want to go too much into the kind of system of how operating systems do this, but obviously, not all addresses, or not all mappings are valid. Just like for a cache, right? You begin your program, the cache is empty, therefore everything is invalid, right? So once the process begins, all of these are invalid. All these mappings are invalid. So what the OS does is when you begin running a process, it will start allocating physical pages in memory for you to work on. So you start your process, you want to use some memory, right? The OS will go and it'll say, okay, great. Well, is there a mapping from the virtual page number that you want to the physical page? And since you just began the process, no, because it hasn't done anything yet. So what the OS will do is it will look inside RAM, and it will say, oh, look, there is room for, physical page number 10 is actually free right now. So I'm going to make a mapping between virtual page number whatever and physical page number 10. So your OS keeps track of which physical pages are free for you to use. Okay? And then access rights are just, we also call them protection bits. This you will be very familiar with. This is if you're not allowed to read to something, you're not allowed to write, or if you're not allowed to execute. For example, I'm sure you're all familiar with the segfault at this point in the class. When you segfault, it's usually because you're trying to write to some invalid address. So what's actually happening is that your computer, it's taking the address that you're trying to access, it's going into the page table, it's attempting to translate that to a physical address, but then when it's looking at the physical page that it corresponds to, it sees that the protection or the access rights there are straight up not allowing you to write to that page, so then it stops you right there. Segfault, you're done. Nice try. Make sense? Cool. Now, to make things even more complex, the page table actually lives in physical memory, which in my opinion is like a what the hell kind of moment, because it's kind of this circular logic of I need the page table to even access physical memory, so how the hell do I even access something? You understand what I'm saying? It's kind of this weird logic. Okay, this is all mediated by a very simple solution. We're just going to add more hardware. So, in addition to the 32 registers that live on your CPU, we also, added a new register, the PC, right? That's an extra register. Turns out there are more specialized hardware registers that we don't talk about. One of them is something called the PTBR, the Page Table Based Register. It is a register whose sole purpose is to keep track of the physical address of where the page table lives. Okay? Kind of weird to think about. So therefore, remember, each process it kind of goes more into like the details here, but each process operates on its own kind of world. It has its own set of registers, it has its own stack, it has its own PC, and it has its own PTBR. And when we switch between processes, there's actually this whole process that the OS does called a context switch, which you don't really need to worry about, but just for more context about a context switch. It saves all of these values, and then it loads them in later. Okay, if that doesn't make sense, it's okay. The point is that we actually keep track. We hard code in the address of the page table itself, and that's how we know where the page table lives for each process. Therefore, Spotify has its own, for example, page table register, base register, that will tell us exactly where does the page table for Spotify live in memory. Therefore, whenever I want to go there, I can just straight up go there, get all my mappings, get my physical addresses, and then, access memory again. Okay? Kind of dumping a lot of information on everybody right now. Is everybody good? Is it okay? Any questions? Really? No questions? Okay, yeah. Yes. Oh, okay. Yeah. Good question. Yeah, that's actually very important to keep in mind. Each process has its own page table, which means what? And you'll see this in lab. The cache lab is a very beautiful lab. You'll see that multiple processes can map to the same virtual address. However, like as an exercise, can multiple processes map to the same physical address? Who votes yes? Who votes no? Okay, very good. Right, that's the whole idea of virtual memory, is to make sure that they don't map to the same physical address. Great. So, I think we have everything here. Mapping, blah, 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 blah. Okay, this tells a little bit more about processes. The point is, everything that we've learned so far in 61C is always under the assumption that we have one process running. So now, just try to generalize. If I have multiple processes running, that means I need to keep the illusion, right? Each process has its own state of registers, it has its own PC that keeps track of where it's executing, it has its own page table base register. There's a lot of information for each process. And somehow there's this really complex piece of software called your operating system that somehow manages to switch between hundreds of these all happening at the same exact time. And it schedules them all to happen to make it appear like they're all actually happening at the same time, even when in reality, they're actually all just going through one CPU, or maybe, multiple if you have, a multi-core CPU. Yeah?
Is the page table done by the assembler or the linker?
Is the page, I'm sorry, can you say that again?
Is the page table done by the assembler or linker?
It's done by the operating system. Yes, this is done at runtime. Yeah. So what's next? Okay, so now let's delve deeper into the page table itself. So, point is, we go inside the page table, we index in. The formal name for what we're grabbing out of the page table is a PTE, a page table entry. But the point is, you should understand what we're getting out of it, right? If we're feeding in a virtual page number, that just means I'm at virtual page number this. I want to know what physical page does that correspond to. And therefore, I just get the physical page number, I get my valid bits, my access rights, et cetera, et cetera, et cetera. Fair enough? Straightforward? Okay, cool. So, let's look at this again. Right, so now when I have this whole process, right, I have two processes. Spotify and my email, for example. I break up all their memory. Now, mind you, neither Spotify nor my email actually know that this is happening. Like, they literally just work with memory like they normally would. But the OS says whenever you make an access, let's say, for example, in this chunk, it actually will correspond to some address somewhere else. So, if we look, we will now have our page tables. Right, so what will happen is, whenever I have a block, this block has its own virtual page number. I think I inverted this diagram. Technically, block 0 will be at virtual page number 0, right, because it's at address 0. So therefore, it should index into, the 0th element of the page table. Small detail. But regardless, it indexes into the page table. It will get the physical page number, and that will just straight up tell it, oh, okay, that actually maps to this physical page instead. Actually maps to physical page 0 in this case. Why? Because we have a free physical page. Right? So as time goes on, as I access more memory, the OS will just keep making these mappings. It will say, oh, okay, you want all this memory? Great. I have this little page right here. You can use this if you want. It's free. It's free real estate, as they say. Good meme, right? I should have put that on the slide. Missed opportunity. Anyway, okay. So when I have process B, right, so the point is, when I have process B, right, I have this last process here. I want to use some area of memory. Well, the point is, after this point, I want to use one more chunk of memory. So therefore, the OS will say, great. So you want to use, let's say, for example, this chunk of memory. Great. I have one more place to use. So therefore, you're good. You can still work in physical memory. But after I fill this up, the question kind of arises. Okay, I filled up physical memory. What the hell happens now? Like, I'm actually out of memory. Does everything crash? Things go away? Not necessarily. Okay, so this is actually where the disk comes in. Actually, let me look at the future slides, see if I can talk about this now. Actually, yeah, I will talk about this now. So memory is filled, so what do we do now? Okay, this is where your hard drive comes in. There's a notion of something called swap space. If you ever look at like the memory usage of your computer, you might see every once in a while when you're running a lot of things at the same time, you might see that you're starting to use something called swap memory. That basically means that your disk serves two processes. Your hard drive, I'm not going to use the word process. That's just going to confuse everybody. It serves two purposes. Okay, one of which is to hold all your information. Your files, your pictures, et cetera, right? That's called the file system. That is totally independent of this. Okay, it's a completely different topic. 162 teaches it, right? And that's kept on your hard drive the entire time. It doesn't go away. But the point is, when I run out of memory in RAM, I can actually go to disk. And I can actually use part of the memory in disk. So therefore, when RAM fills up here, that means that I no longer have any more room for physical pages. So what happens? Let's say, hypothetically, I want to allocate one more room of space. Let's say, all of a sudden, I want to load Word at this address. Okay, well, currently, nothing's being used there. So when I attempt to go to this virtual address, it's going to look for a mapping. Currently, there is no mapping for that virtual page, right? So then what's the OS going to do? It's going to say, okay, well, let's try to find a mapping. Let's see if I can give you some free real estate to work on. Well, is there any real estate to work on? No, there isn't. So then what happens? Well, through some very complex process, the OS actually keeps track of where in disk we can bring in free pages from. So what will it do? It will evict a physical page from RAM, push it back to disk, and bring in a clean slate. It will bring in a clean page for us to use now. Does this scheme of eviction sound familiar to you? It's almost like caches. And we could almost consider that just like how we have caches and RAM, we could almost consider RAM to be a cache for disk. I mean, if I got less oohs than I expected, so ooh. Point is, it's the same process, right? In a cache, when you run out of space in your cache, what do? You have to make room for it. So you evict something, you move it back further in the memory hierarchy, and then you bring in something new. The same thing happens here. When I'm out of physical space, when I'm out of RAM, I have to evict a page. I have to put it back on disk, and then I have to bring in a fresh page to work on. And the OS keeps track of all of this, right? So later on, let's say I want to bring in that old page again, it will bring in the old page. So it keeps track of the dirty pages that got written to, it keeps track of free pages that we can bring in, it keeps track of all of this stuff. Do you need to understand how it does this? Absolutely not. Not for this class, at least. Yeah?
Since page tables live in RAM, does that mean that we can only have a fixed maximum number of processes running?
Well, you can't have an infinite number of processes, because obviously that wouldn't work. But if you really want to think about it, your page table, well, there's also, as we'll get into the future lecture, Mickey will talk about multi-level page tables and things like that to prevent there being too much crowding. But the point is, your page tables live in physical memory, which technically means that if you have too many page tables can also get written back to disk as well. It's kind of weird to think about. I wouldn't go down that rabbit hole because it'll just be confusing. But the point is, yes, there's a theoretical limit, but your computer will work its hardest to ensure that that won't happen. If you have too many processes happening at once, what happens? Your computer is really slow. Why is it really slow? Because it constantly needs to be bringing in new page tables, loading in new things. There's a lot of swapping and a lot of moving around of memory. That's why things get really, really slow. Yeah. Any questions? Oh, yeah.
Is this safe? You just get a chunk of other processes memory? Maybe there's some important information.
Well, see, the key is that we never do get a chunk of some other process's memory.
Let's say my RAM is DRAM is
Yeah.
and I need some other page.
Yeah.
Right? So the OS will write, let's say, page 2 to this, and then it will give page 2 to me.
Mm-hmm.
Right? But page 2 was for some other process, and now I have access. That could be.
That's a very good point. So what happens is when page 2 gets written back to disk, it gets written back, and the OS actually keeps track. It's actually in a table. It tells it, okay, this corresponds to this process, and it stores information about which process it corresponds to. Okay, so therefore, as long as the new page 2 is in there, it will assume that page 2 is correct. But then when I bring in the new page from disk, it's no longer page 2. Okay, page 2 is literally just the position in here. Like this is physical page 0. That's physical page, this is physical page 0, physical page 1, 2, 3, 4. Right? So it's all about where these pages get placed. So a page gets evicted. When this page 0 gets evicted from physical memory, it becomes a nobody. You know, it doesn't know its identity anymore. All right, it just gets pushed back to RAM or to disk. And then when we bring it back into disk, we move it into wherever it wants to become, and then it will become whatever appropriate page number it becomes. So hypothetically, page 0 can get evicted, it can go to disk, it lives in disk for a little bit, and then it comes back later, and maybe the only place for it to come back to is here. So maybe now what used to be page 0 now becomes physical page 5, for example. Does that make sense?
Does make sense, but it doesn't answer my question.
Okay, sure. All right, so let's kind of big picture here. Why are we doing this? Why does virtual memory matter? It all comes down to I need to run multiple things. All right, that's the entire point of this. The idea that your computer is just one piece of RISC-V code running, one after another, just doesn't really make a lot of sense, especially when you have a lot of programs that are running at the same time, like they're dynamically running, right? Like, it's not like Spotify is compiling every 1 second, and, I'm constantly loading in a new program. Like, it doesn't make sense, right? So I need to have a lot of processes running, but I really, in reality, hardware-wise, I only have one, piece of RAM. So how do I mediate between this? And the idea was provide the illusion. Okay, so what guarantees did I have? Well, I want to make sure I have shared memory with protection. So therefore, each process should be allowed to write to wherever the heck it wants in memory, right? And it thinks it is. But the point is, the VM is taking care of the case where they will never touch each other. Okay, yeah, you both are welcome to write to the stack, but in reality, you're actually writing to 2 different places. Okay, so we're protecting processes from each other. That way, one process will not modify the code of another or the data of another process. Separate address spaces, and memory hierarchy. We'll get to that in a bit, but it's kind of a law right now. Are there any questions? No? Yeah?
So how large is the virtual?
How large is virtual memory? Excellent question. Let's think back. Let's forget this lecture. All right, I want you to forget this lecture. All right, if I tell you that I have a 32-bit address space, how much memory do you have? There you go. That's the virtual address space.
So basically, we still have the illusion that they have a whole piece of the RAM.
Exactly. Exactly. Right. Like, you think about it, a lot of computers say, like, oh, I'm a 32-bit system, I'm a 64-bit system, but they all have different amounts of RAM, right? So how do they actually all map to the same thing? It's all through virtual memory. Each process operates on the assumption that it has the 2 to the 32 bytes to work with, but in reality, you might have much less, you might have much more. Who knows? Okay. Good question. Okay. So, all right, take a little break right now. Talk about imminent trivia. You have a midterm tonight at 7 p.m. I hope your cheat sheets are in. Take a look at the cheat sheet that we posted. That way you don't need to write anything extra on yours. That's like important real estate on your cheat sheet. I think, I don't know if I'm allowed to say this. In my personal opinion, I think it's a fair exam. Can I say that? Okay, it's a fair exam in my opinion. Definitely some hard questions on there. Definitely some beautiful questions on there. So, yeah, beautiful questions. I think you all do great. Okay, like looking into the future, so the fires definitely kind of screwed up our schedule a little bit. As a reminder, no more lab deadlines are pushed back. Labs are still due the same time. There was no lab checkoff this week. Lab 9, the caches lab, is due next week. Discussion next week will be on virtual memory. You have a homework that's been released on caches. Oh, okay. I will make a note of that then. The autograder is not up yet for Project 3.1. Sorry. There's a lot of work that goes into making these autograders. Anyway, okay, so the caches homework is due next Thursday. It is excellent practice. I would argue that our material on caches, lab, discussion, and homework is very good, for learning how caches work. So I highly encourage you to ask questions about it, because caches tend to have a very steep learning curve. Your Project 3.1 is due 11/6, not 11/8. I do apologize for that. It is definitely much shorter than Project 3.2. Okay, so please do not save it to the last minute, because you want to get started on Project 3.2 as soon as it's released. I would argue the ratio is this maybe takes 1/10 of the time as Project 3.2. Okay, it's like a really big thing, because Project 3.1 is you implementing solely the ALU and the rec file, and then Project 3.2 is the entire rest of the data path. The entire rest of the data path, which is much, much more. Okay, I think it's a cool project, though. I think you'll really understand how the data path works after building it yourself. Okay, like there's no better way to understand something than building it yourself. Yeah. Project 3 comes out when we're ready with it. We're currently still tweaking it. Sorry about that. Yeah. So hopefully as soon as possible. Hopefully, I guess by the weekend or like early next week latest. Yeah.
Do you have an average hour count for Project 3.1?
For Project 3.1, I would say 4 hours. 4 hours, yeah. Like that's accounting for like lots of some bugs and like annoying wiring stuff, but yeah, 4 hours. Yeah. All right. Any other questions? All right, great. As a thank you for everyone coming to lecture today, I want to share with you one of my greatest creations that I made. This is also to get you hyped for Project 3.2. So Dan has that beautiful picture of the creation of Atom, and I kind of built on that. So this is the creation of the computer. So this is to get you hyped for Project 3.2. So here we have, I'll explain everything here, right? So here we have Dan, who comes from a hardware background. And here we have Mickey, who comes from a hardware background. We have Dan from a software background. These are some of the TAs who we're helping out, making Project 3. So, we're kind of like the angels in this case, little, cherubs. And then this guy in the back, kind of like the Holy Spirit of this, that's Dave Patterson, if you're not familiar with him. Dave Patterson, A, wrote one of your textbooks, and B, is kind of like the godfather of this class because he basically helped invent RISC. He teaches 152. He helped design this class, and he won a Turing Award 2 years ago for his work on RISC-V. So he's kind of like, his shadow will always be covering us. So, this will be posted on the 3.2 spec, so don't worry about it, but I hope this gets you excited because honestly, you're creating a computer at this point because you understand, the hardware-software dynamic. Yeah. Very proud of this, Turns out Photoshop has very excellent tutorials, so props to Adobe for making good Photoshop tutorials. Yeah. Do you want to take a break, or do you just want to, trudge through the rest of this? Just finish it up? Okay, yeah, actually, you guys can leave early, go study for your exam. Okay, so let's compare caches to virtual memory. Part of the reason in previous semesters, we actually had virtual memory at the end of the class, and we moved it earlier because we think there's a nice parallel between... First of all, that's a nice hint for what's going to come, foreshadowing. Parallelism is the last module of this course. But we're trying to show a nice parallel between caches and virtual memory. So it's kind of like a little test right now. Okay, so in caches, we have blocks and lines. Okay, and the analogy to that is a page, right? For caches, we bring things in terms of blocks, right, which is by design. And for virtual memory, it's the exact same thing. By design. You can actually look on your computer what the size of the page your computer is using. Okay, and we divvy up memory in these pages, 2 kilobytes. They're pretty big, right? We don't want it to make it 16 bytes like a cache block. We want to give it enough real estate for the process to work with, okay? But we don't want to make it too big because as you learned about maybe in a previous lab or as you learned about in the cache lab, moving a ton of data at one time is a very, very slow process. So again, it's a trade-off. All right, if you miss in a cache, you have to go back to RAM. When we miss in RAM, right, and when I miss in virtual memory more specifically, I have to go back to disk and get that. And we call it a page fault. Okay, that's just the nomenclature for it. You miss in RAM, which is the equivalent of not having an appropriate mapping from VPN to PPN. You need to go to disk, get the appropriate page, create the mapping. All right, let's see what else. Block size, yeah, page size, placement. I'm not sure if I fully agree with this term, a fully associative. So we know about direct map and n-way set associative caches. As a quick reminder, for one-way set associative is direct map, n-way is just however many ways. And if the number of ways equals the number of blocks, then that's a fully associative cache. I would argue personally, I don't know, maybe Steve, you help me. I would argue that a page table is a direct map cache. I mean, each index does correspond to one page table entry, right? What do you think, Shruti? Yes? Direct map? Okay, we'll go with direct map cache then. I think it's more of a direct map cache, right? Because there's no business of any of these, indices and sets and whatever. Point is, you have a virtual page number, 5. You straight up go to the 5th entry in your table and you just look. It is that simple. There's no need to overthink this. Okay, as an exercise, this might help for caches as well. If I have, let's say hypothetically, I have 5 bits of virtual page number. When I break up my addresses, I break it up into offset and virtual page number, I have 5 bits for my virtual page number. How big is my page table? It's 32 elements. Why? Because with 5 bits, I can represent 32 things. So therefore, I can represent 32 virtual pages. Each virtual page needs its own mapping from VPN to PPN, so therefore, I just have 32 entries in my page table. Make sense? Okay. All right. LRU random. Oh, okay. Yeah, I mean, it's relatively straightforward. When we miss, when I'm out of memory in RAM, how do I decide which page gets evicted and pushed back to disk? It's just whichever one was the least recently used page. That should kind of make sense, just from a logical standpoint. If you don't use the page, why keep it in RAM in the first place? All right, cool. Yeah. Okay, so I kind of touched on this earlier, but the point is, okay, fragmentation problem isn't really that important. For swap space, I mean, the idea was the disk serves two purposes. One, it holds all your files, permanently. But two, when you're running out of RAM, it is basically served as like the RAM for your RAM. It's the backup for your RAM. Caches need to go to RAM when they fill up. RAM needs to go to disk when it fills up. Okay, that's it. And we just call that area of disk that we use for like extra RAM swap space. Okay. Grow a process as an operating system, blah, 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 blah. You guys all know this. Oh, yeah.
So does that mean the virtual memory matching function is not using hardware, but it's part of OS?
Yes, it's part of the OS. Yeah. One thing to keep in mind, though, is that unlike a cache, which is a piece of hardware, a page table is data. Okay, so it's not like we're building a separate piece of hardware for the page table. Remember, it's just a piece of memory that lives inside physical memory itself. Okay, that's something to keep in mind. It's not that important, but it's just, know about it. All right, so let's talk about, okay, in the previous slide, I talked about, why would, processes need to grow, et cetera, et cetera, et cetera. Yeah, the point is that, okay, we have our image of memory before, right? Your stack can grow, your heap could grow. Like, from a big picture point of view, okay, do I want to allocate all this information, in physical memory? No, not necessarily, right? When you begin, your stack doesn't really have much on it, and your heap is essentially empty at the very beginning. So therefore, you should only be allocating pages in physical memory as you need them, right? Oh, I'm going to use this piece of memory. Okay, great. Allocate a page at the bottom of the heap for that. And then as your program grows, you malloc more, et cetera, et cetera, et cetera. Great. Okay, so therefore, I just need more memory. Give me another page to work with, right? So we just do things on a need-to-know basis, right? I give myself pages as I need to know that. Fair enough? I feel like we're just kind of hitting the same concept over and over, but it's important that you understand it, because this is a very, very important concept in general. Okay, for like in your coding career, knowing how virtual memory works is the whole reason why your computers work. The whole reason why you can open up, like you can have your 30 Chrome tabs open at the same time is because of things like this. Okay. That is true. That is true. If something fails, it won't crash the entire computer because each process can operate completely independently. If a process crashes, what do you have to do? Just invalidate its page table. There you go. Just free up all the memory that it was taking up. No problem. No other process gets affected by this. Right? That's nice. From a security standpoint, that's also very nice. Because if you hack into one program, you're trying to make it as hard as possible for that program to affect another program. Right. Take 161 if you're still interested. So let's talk about problems. Now we're going to be really building up on this, and things are going to get ugly now. Okay? So the page table lives in memory. We had a cache for normal memory. It turns out that going to the page table is a really inefficient operation. And somebody asked about this earlier. When we have to go to the page table, I'm going to switch back and forth between these two slides. You're going to ignore what TLB is for now. Okay, when I need a virtual address, what do I have to do? I have to get the virtual address from the page table. But where does the page table live? All the way in main memory. So therefore, I have to go all the way to main memory just to get the mapping from the virtual address to the physical address. And then from the physical address, I can continue bringing things into memory, right? By either going into my cache, et cetera, et cetera, et cetera. So that actually means that I need to access physical memory twice per one virtual address access. Does everybody see why that's the case? Right? If the page table lives in physical memory, I need to go there first just to get the actual address that I care about. So you're going to main memory to figure out where in main memory you should even go. It's kind of a weird process. So what's the big idea here? What's the big brain move here? What if we had a cache? This is kind of like an idea somebody would come with like when they're high or something. What if we had a cache for our page table? Okay, so that is what is called a translation lookaside buffer. It is a cache with the specific purpose of being for the page table. So this is independent of the normal caches that we dealt with last week or like in the previous lectures. However, it operates in the exact same way. TLBs are usually fully associative caches filled with page table entries. Okay, so what does that mean? That means that from now on, whenever I want something, What I first do is I look and notice how I'm not going to zoom into the TLB and how it works because I want you to have a big idea of how caches work. You feed it something that you want, and then you should be able to spit out what you want from it, right? So I'm going to feed it the virtual address, and I want this TLB, which is the cache, to give me the physical address. If it has the mapping, then great. I don't need to go all the way to physical memory to get my mapping from virtual page number to physical page number. I have it already in the TLB. So therefore, if it hits in the TLB, I got my physical address, and I can just straight up go to memory, right? And you can black box memory as the whole cache, L1, L2 thing. Okay. If I miss in the TLB, that means it's straight up not there. So therefore, what do I need to do? Just like how for a cache, when I miss in the cache, I need to go to memory and bring the block in. When I miss in the in the TLB, I need to go to the page table, find the appropriate page table entry that I was looking for, and bring it into the TLB and load it there. It's just like a normal cache. But the point is, it exclusively deals with page table entries. Does that make sense? Great. So, now there's definitely a lot of confusion that could arise from this. If the TLB misses, does it actually go to the cache for the page table entry or the main memory? Blah, blah, blah. You can look at past final exam questions if you're curious about this. I think we had one once. It was a really ugly question. But the point is that it was really inefficient to go all the way to main memory, so why? Okay, instead, just straight up build another cache. One thing to keep in mind, though, page tables are they're not actually physical. We don't build a physical page table. However, we do build a physical TLB because we build physical caches. So therefore, a TLB is a physical piece of hardware, and a cache is a physical piece of hardware. And main memory is its own physical piece of hardware, right? And we have to interface between all three of these in order to get my address. Does that make sense? I think in the next lectures, Mickey will go over how TLBs work and how the whole process of translation works more in detail. But from a high level, I hope you can appreciate why we have all of these processes, right? We have the whole idea of virtual memory. That way we can have this mapping from virtual addresses to physical addresses. That's a slow operation. So just smack a cache on it, all right? Just throw a TLB in between it. It makes things faster. That's the whole idea behind a TLB. In lab, you'll have an excellent example where you'll see how these things kind of work. So let's, hopefully by now, I've kind of drilled in the same points over and over to where you'll be able to answer this question. So, given both of this, okay, I guess I'll just ask them one at a time. There's no need for a Google form. I didn't make one. So, okay, raise your hand for true and false when I ask. So, locality is important, yet different for cache and virtual memory. Temporal locality is important for caches, but spatial locality is important for virtual memory. I'm going to append to this question. I'm going to say both temporal and spatial are important for caches, but only spatial locality is important for virtual memory. I'm going to think about this. All right. Is, for A, spatial locality relevant to virtual memory? And B, is temporal locality relevant to virtual memory? Okay. What do we think? Who thinks true, only spatial locality is relevant to virtual memory? Okay. And who thinks false? Okay. Now, are you saying false as in like both are important, or spatial locality is straight up not important to virtual memory? Okay, yeah. So they're both very important. Why? You can just think about it, right? When I'm working in the same area of memory, load word from this address, load word from this address. Point is, you're working in the same area of memory. So therefore, the pages take advantage of that locality. And same thing for temporal locality. Oftentimes, when you're working with a stack, chances are you're going to be working with that same area in the stack for the duration of that function. And then when you return, you're done, right? You're not going to be moving between the stack and static all these different times. When you're somewhere in memory, usually you're going to stay there in memory. All right. And the second question is, VM helps both with security and cost. Okay, I'm just going to say yes because it's kind of like a leading question. Of course it helps with security and cost. It helps from security. Why? Remember, it separates our processes. That way they don't even know that somebody else is running. All right. So it makes life a lot easier. I think that's all I have to say. Yeah. So in conclusion, big points here. I want multiple processes to run. Okay. Processes should not need to be affected by this process. Therefore, I have this mapping of virtual memory to physical memory. They can all run independent of each other. Okay? If this is a slow operation, I just throw a cache in between it to make things faster. This is how your computer is able to run all the programs at the same time. It's a pretty cool concept in my opinion, and there's definitely a lot to delve deep into how these things are implemented. There's actually a lot of theory and a lot of research that goes on as to how do we make these as efficient as possible. All right, that's it for today. Best of luck on your midterm tonight, everybody. If you have any questions, I'll be outside and